Okay, guys, so how we doing? All right, so let's do a state of the semester. Assignment 1 is graded for everything that's turned in. Okay? So 10 of the 13 of you have turned that in and have gotten that grade. Okay? Assignment 2, 6 of 13 have turned that in. Graded, yes. Graded, yes. Okay? Assignment 3, which is the first one we're doing SolidWorks, 2 of you have turned that in out of 13. So I haven't bothered to grade that yet. And assignment 4, 1 of 13 has turned that in. Okay? I'm just saying that's where we are. You know, summer is vanishing quickly. I don't know if you guys feel it yet, but I'm warning you, July 21st is going to be here in 6 weeks. Okay? So I have 3 people that haven't turned in assignment 1 yet. And we're 4 weeks in, 5 weeks in to the summer semester. Okay, so if you're one of those 3 people, I'm very, very concerned. Okay? And I'm also concerned because we don't even get to SolidWorks until this one. And if you're struggling, then these additional assignments are just going to compound upon that struggle. So I had a debate last night of whether even to give you assignment 5 because, or even talk about something today, because my thought is I'm talking about something that's 3 assignments further along than you're even at this point. Okay? So my thought kind of is I can give a lecture and a whole bunch of you are thinking back here of how do I do a hand calculation, or not a whole bunch because it's just 3 of 13, but some of you are still thinking about how do I do a hand calculation of inverting a matrix. Okay, so I'm talking about something in SolidWorks and you haven't even done the beam stuff. Okay, only 2 of 13 have turned something in. Now, I realize that some of you are working on it. I can see right now that some of you are currently working on it. But my dilemma, of course, is I can be talking about I'm trying to talk about more and more advanced capabilities in SolidWorks, and if you haven't done the beginning stuff, you don't have any idea what I'm talking about. Okay? So that's my dilemma is I don't want to be talking about stuff that you're going to get to in 3 weeks, and then by that time you're not going to remember what I told you about. Okay? So I'm going to go ahead and give you a little bit of an intro to what we're doing with plates and shells. But I really need you guys to catch up on getting these assignments in. Because the problem is, like I said, is I'm going to be talking about stuff here in class, and then you're going to go back to early assignments that we talked about a couple weeks ago. And you're not going to, you're going to be doing stuff disjointed at different times, and it's not going to click. Okay? The other side of that is these 2 assignments were pretty much just do the math and turn it in. Okay, those were pretty easy. Starting with this assignment, there's the do a hand calculation, do a SolidWorks calculation, compare the difference between the 2. And historically, I start to get lots of struggles with what is it that I'm supposed to turn in, how am I supposed to turn in these lab reports with these 2 assignments. And so I'm worried about what you guys are going to be turning in, and I'm expecting that we're going to we might even have some iterations of these where I'm going to give it back to you and say, I'm not grading this. You got to do something more in line with what I asked for. Okay? So all that being said, I would really like these numbers to be getting up a little, like, everybody getting stuff turned in so that I can give you the appropriate feedback so that we can learn something. Okay? These assignments are kind of building upon each other, and I expect to see, I've set these up so that there's a continuation of similar problems where we're doing things different ways, and we're hopefully learning something from those. And if you haven't done the assignments, then obviously we're not going to learn from those incremental advances yet. Okay? So please, 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 even though I told you we could turn things in kind of casually, we kind of, if we're going to, learn the best we can, we need to get this stuff turned in so that we do the learning. Okay? All right. So I'm going to go ahead and talk a little bit about plates and shells, and I'll talk a little bit about what I expect you to do in assignment 5. But I'm going to keep it brief because I'm kind of thinking I'm going to have to say this all over again as you guys get to chapter 5, or assignment 5. All right. Any thoughts before I start on that? All right, so I've got a little bit of kind of background information here. We are moving on with assignment 5 to 2-dimensional elements. Okay, so assignment 3 and 4, you should be doing 1-dimensional elements, right? So I specifically told you to use the weldment tools, which results in beam elements in SolidWorks. And so you should have finite element models that just look like sticks connected together. Those are 1-dimensional elements. So assignment 3 is 1D or beams. Assignment 4 is 1D beams. Assignment 5 is going to be 2-dimensional, which we'll call plates and shells. Okay? So if you remember back to early on when we were talking about different element types, we have 1-dimensional elements, we have 2-dimensional elements, we have 3-dimensional elements. General good practice is use the simplest type of element that you can, because it's going to reduce the amount of modeling that you have to do. So in the case of assignment 3, assignment 3 has a truss on the second part, if I remember correctly. Then a truss is a really good example of use beam elements to connect that together, and you'll keep your models as simple as possible, which will hopefully make your life a little bit easier. Okay? All right, so we're starting to talk about 2-dimensional elements. So I put some stuff up here. My dilemma is kind of how much theory to give you versus how much just practical, this is how you solve the problem kind of stuff. Okay? Because ultimately, at the end of the day, we all want to just get the answer, right? So I put a little bit up here because this is a little bit of theory. Because I want you to have an awareness of this. Plane stress versus plane strain. It's probably not something that's just going to roll off your tongue. In my opinion, it's a little bit abstract. But I think I wanted you to see it a little bit. Okay? So you guys should be familiar with this equation. What do we call this? Read the title. This is Hooke's Law, right? We've done this time and time again. This is the same F equals Kx type equation, right? Hooke's Law. So stress is equal to modulus elasticities times strain. If we want to rearrange that, we can say strain is equal to 1 over modulus elasticity times stress. Okay? Back in 211, we use that equation. And we always were doing one-dimensional stuff. And so we just have a simple linear algebraic equation that expresses those things. Okay? We get to 2 dimensions, a biaxial state of stress. So think about scenarios where we have forces that are pulling down the length of something as well as pulling crosswise on it. We have stress in multiple directions. A really simple example of that is think about a balloon. If you inflate a balloon, it has stress that is going in 2 directions. Or, typically simplified down to 2 directions. But essentially you have an infinite number of directions as the balloon stretches because of the pressure inside of the balloon. So if we want to use a biaxial state of stress, 2 directions of stress, we have taken this equation up here and expanding it into 2 axes. We have strain in the x direction, strain in the y direction. We have shear strain. So these 3 values would be the strain values. My relationship for the stiffness would look like this. And now we see that we have some modulus elasticity, and we also have shear modulus. You guys should have seen shear modulus back in 211. Okay, G is the shear modulus, which is different than the value E, which is modulus elasticity. Okay? But all of these expressions are a relationship of how much does it deform. And then these are our stress values. Stress in the, axial stress in the x direction, axial stress in the y direction. And I've got it overlapping my Purdue logo there, but then the shear stress. Okay? So, this is plane stress. And we have to relate all these, and if you remember, we have some complications with Poisson's ratio here, because remember, if I take a tensile element, I have just a simple tensile specimen. If I put it in uniaxial stress, where I'm just pulling it in one direction, when I pull it this way, it obviously gets longer, right? So we have strain. So we have strain in the, we'll call that the y direction, right? So strain in the y direction. What else happens when I pull this tensile specimen? It's thinner, right? So forces in the y direction also causes, I need to reverse my direction. Also causes strain in the x direction, right? So when I start talking about a biaxial state of stress, these Poisson's ratio divided by modulus elasticity terms are in here because the forces that are in the x direction are causing strains in the y direction, and forces that are in the y direction are causing strains in the x direction. Okay? So this becomes a matrix instead of just a simple algebraic equation. Okay? So I'm just trying to show you a little bit about it so that if you see this somewhere, you have a little bit of a better appreciation of why do I have Poisson's ratio in this equation, and so forth. Okay, so we also have a concept known as, continuing on that concept, so for plane stress, we use this approximation a lot when we have thin bodies. And the reason I'm bringing all this up is because we're talking about 2-dimensional elements. And for cases where plane stress is applicable, then I can use a 2-dimensional element. Okay? So, if I have a body where the thickness of the structure is small, I can assume that it is subject to plane stress, and I can simplify my equations. It makes my analysis a lot easier. All right? So, an arbitrary definition of a thin body is that my thickness is less than 10% of its length. So the balloon that I used already would be an example of something that's subject to plane stress because its thickness is very, very much smaller than its overall size. A propane tank would be the same thing. We can expand this to a lot of other things. When I was working in industry, almost everything we built was made out of 1/4 inch or 3/8 inch thick steel plates. And so we did almost all of our analysis, assuming plane stress, and we just modeled all of those plates as two-dimensional elements. Okay? If we were, say, doing an analysis of an automobile, the body of the car would definitely apply to plane stress. Probably even the frame of your car. I don't know how many of you have actually looked at the frame of a modern car, but the structural elements of most vehicles are thin sheets that are folded and formed to create structural shapes. And you can model all of that as two-dimensional elements that are going to be subject to plane stress. Okay? Think about the I-beams on the Kennedy Bridge. If I didn't want to model them as beam elements, then I could look at the I-beams, and rather than modeling it as a three-dimensional object that has thicknesses, I could simplify all of the structural pieces down to 2D elements that have a constant thickness. Okay, so this is a really useful tool. So I'm pointing out that there's lots and lots and lots of applications where you can use this concept. Okay? Places that you can't use it would be places where the thickness is going to be important or the thickness is going to be variable. A baseball bat. I guess I'd have to qualify that further as what kind of baseball bat. Okay, a wooden baseball bat, you would not model it with plane stress and elements. An aluminum one, yeah, you might be able to do it with plane stress because it's a hollow object, right? Okay? Everybody understand? Kind of situation I'm talking about? Okay. The loads are in plane. So the loads are in the plane themselves. So back to the balloon idea. The forces that are in the balloon, the loading is stretching the balloon. So they're in the plane of the object. Okay? When I do all of that, I assume that the stress in the z direction is 0, and the shear stresses that are associated with the z direction are 0. And when I do that, then my equations become simpler, and all of this gets worked into the formulation that SolidWorks is going to use in order to solve these models for you. Okay? Put a little note on here. Again, I need to adjust my slides so it doesn't overlap the text, but notice that my stresses in the z direction are 0, but my strains are not because of Poisson's ratio. So just keep that in mind. So, one objection you might have is, I did this result, so I assume that it's thin, but I'm still getting strains in the z direction. Well, yeah, mathematically, there's still strains in the z direction because of Poisson's ratio. But we're assuming that there's no loading in those directions. Okay? All right. The other type of scenario that we might look at is called plane strain. And this applies when I have thick structural members. So if I have a thickness that's greater than 10% of the length, then I can simplify things using plane strain. I assume that strains in the z directions are zeros, and it's just a different approach. The biggest thing is I want you to understand that there are some simplifying things that we can do in these two scenarios. One of them we call plane stress. All the stresses are 0 in the z direction. The other we call plane strain. All the strains are 0 in the z direction. But 0 strains in the z direction does not mean 0 stress in the z direction. Okay? So that's the distinguishing difference between the two. So, Let's start talking about finite element models. We're talking about two-dimensional elements. These two-dimensional elements are going to be triangular shaped or quadrilateral shaped. They're going to have nodes at the corners, and the nodes are where everything is, all the connections are made, where all the forces are applied, and so forth. So for example, if I have a distributed load along the edge of the element, the only places I can apply loads to anything in a finite element model is at the nodes. So I have to change my distributed load to concentrated loads at the particular nodes. Okay? This is a little bit of a theory thing again, because SolidWorks does this for you. But I want you to understand, as you're putting the loads in, kind of what it's doing. So if you tell SolidWorks that you have a distributed load, what it's going to do is take that distributed load, break it up into lots of little concentrated loads, and apply them at the appropriate nodes in your model. Okay? Same thing happens with weights. So if you put weight of your model in there, depending on the type of element, it's going to distribute that weight differently across the nodes. Again, this is kind of behind the scenes. You don't have to worry about it too much, but I just want you to understand a little bit about how the loads get from the load that you tell SolidWorks is being applied to the actual nodes and elements. Because from your perspective, when you're using SolidWorks, you're not going to see that happen. It just does it for you. And what we're doing is trusting that SolidWorks has programmed that correctly so that it works. Right? So there's a lot of stuff going on behind the scenes, and that's part of the reason I've tried to emphasize with you is be very, very skeptical of your results. You need to double check your results to make sure they make any kind of sense. All right, so we're going to talk about a couple of different types of elements. You guys will know more about what these means as we go along here. A CST is a constant strain triangle, a quad 4 or quad 6, a linear strain triangle, and a quad 8. Those are different types of two-dimensional elements. And we'll talk a little bit about each of those in a minute, but that's a brief introduction to those. So, something that I haven't made a big deal about yet is the difference between exact results and non-exact results. With our beam elements, so the assignment 3 and 4 that we've done, we should be getting exact results. In other words, our hand calculation should match our FE calculation, assuming that we have constant cross sections and all those kinds of things. Okay? So what does that mean? Thinking about back to beams. If we did a tapered beam for the homeworks, but let's assume we just have a straight beam with a constant cross section, and I put a load on the end and I calculate what the deflection of that is. Right? We can do a hand calculation to come up with this deflection value. Right? I can also model this in SolidWorks using the weldments tools and so on that we've shown. And assuming that this is a constant cross section, and we have put the same force in there, then our delta FEA should exactly equal our delta hand calculation. Because for our beam elements, our beams are exact, and our answers should be perfectly equal to each other. Okay? That's what an exact result means. As we go along these two-dimensional elements and three-dimensional elements, sometimes we will get exact results, and sometimes we won't. Okay? So that's what I'm saying on this slide. we will get exact results in the IIF, that's if and only if, these conditions apply. Okay? So, the stress and displacement fields have to satisfy equilibrium. What does that mean? What's equilibrium mean? Guys have all had statics. What did equilibrium mean? What? Everything's equal. Everything sums up to 0, right? So, if our stress and displacement fields sum up to equal 0, then our results will be exact. If our boundary conditions sum up to equal 0, then we will get exact results, and if our elements are compatible. And what is compatible? Compatible means that there's a simple way of visualizing this is no gaps between elements and no overlaps between elements. So this is a little bit abstract, but what happens is that most of our element types do not meet these first two conditions. Okay? So, most of our element types, our formulation, remember our element types are a mathematical representation of physical reality. Our mathematical representation is we're trying to get as close as possible to reality, but invariably we're making some assumptions. And because we're making some assumptions, then that means it doesn't match reality exactly. And what usually happens is the equilibrium is not perfectly maintained. And if it's not, then we're not going to get exact results. Likewise, our elements may have some overlaps and may have some gaps. The mathematical creation of the mesh is not completely perfect. Okay? So, the message to you, the practical implication of this, is that with two-dimensional results, our delta FEA, so 1D, this is usually true for 2D, our delta FEA is usually not equal to our delta hand calculation. Now, usually it's close, but it's not going to be perfectly exact. So we're going to start talking about stuff like mesh refinement. The smaller the mesh size we use, the better our results are going to be. And that's why you should take your first result and look at it skeptically, and then maybe try another analysis and see if you get a little bit better results. Okay, so we'll start working on mesh refinement as we go along. Okay, but what I want to emphasize to you is that your answer is not going to be perfectly correct. There's going to be a little bit of error there, and as we go through these assignments, that's going to be one of the important things that you report is how different is your FEA results from your hand calculations. And hopefully as we go along, we get those smaller and smaller. Back on your tapered beam, I asked you to model it with 1 element, 2 elements, 4 elements, and 8 elements, I think. Okay, that's not going to be an exact result because of that taper. Right? Remember I said these exact results happen with beams when I have a constant cross-section. That tapered beam does not have a constant cross-section, so our answers are not going to be exact, but as we get more and more elements, we should be getting closer and closer to the exact result. Okay? All right. So, we're going to have to start doing something called mesh refinement. There's 2 types of mesh refinement. There's N-type mesh refinement. I like to think in my head, N refers to number. So we're increasing the number of elements, the number of nodes, and we're getting closer and closer to the perfect result. With that type of refinement, obviously, if I do an infinite number of nodes and elements, I should get a perfectly exact result. Obviously, an infinite number of calculations is not going to ever happen in a finite period of time, so I can't ever get there, but increasing the numbers until I get a good enough answer is desired. Another type of mesh refinement is called P-type, where we are increasing the complexity of the element shape. So P stands for polynomial of sides. And that type of refinement, the number of elements stays the same. The equations that define the sides of the element get increasingly complex. Okay? So I think you guys are familiar. So let's say that I have a triangle, and if each side of this triangle is a straight line, how do I write an equation for a straight line in math? This is one of those equations that everybody's supposed to know.
Y equals mx plus b.
Yeah, exactly. Y equals mx plus b is an equation of a straight line. Right? Okay? So if I have linear sides, then my equation looks something like this. If I increase the polynomial of my definition of the line, if I integrate this once, what do I end up with? I get a triangle that has parabolic sides, right?
Yeah.
And what does that equation look like?
Oh, you have the x squared term.
Y equals something x squared plus something x plus a constant,
Yeah.
right? And what I'm doing here is I'm increasing the complexity of the definition of the side by increasing the polynomial of the definition. So this is linear, this is parabolic. If I do that once more, I get y equals something x cubed plus something x squared plus something x plus a constant, right? And so polynomial refinement, we keep increasing the curvature of that shape until we get something that fits. You might have done that before with a lab data on a graph. You ever done you do a line fit to your data and it doesn't look very good. So then you do a parabolic curve and it looks a little bit better. Then you do a hyperbolic curve and it gets closer to the actual shape. Okay? Similar kind of thing that we're doing in the software. Okay? So two types of refinement, you need to know those. And concept-wise, I already put the answer up here for you, but SolidWorks uses N-type refinement. So if we're going to increase the number of elements, then you have a control, there's a slider control where you can specify how many elements or what size elements do you want. And as you slide it so that you get more and more elements, you should get better and better answers. Okay? All right. So, make sure you know the difference between polynomial and N-type mesh refinement. We need to talk briefly about the various types of elements. I mentioned already the constant strain triangle, the CST. The sides of the triangle remain straight. The name comes from the fact that the strain across the triangle is going to be constant. And this element type works okay as long as I don't have changing strain across my structure. The problem is these get really, really bad when I have something that's undergoing bending. Okay? So what does that mean? Well, think about if I model, trying to just use simple things that you guys are familiar with. I've got a cantilever beam, I put a load on the end, it's going to bend down, right? What is the stress on the top?
Tension.
It's in tension. And the equation would be sigma is equal to MC over I, right?
Yeah.
Okay, so you guys have seen that equation before, even if you didn't remember at the top of your head what it was, right? At the neutral axis, down the center of this, what is the stress?
0.
0, right? The whole idea of the neutral axis is 0 stress in the middle. And at the bottom, what is the stress? It's in compression, right? And it would be sigma is equal to minus MC over I. So it goes from a max value, max positive value at the top to 0 down to a max negative value. That's a strain or a stress gradient, also a strain gradient. So if I use CST triangles, so if I broke this beam up into lots and lots of little triangles and used a CST formulation, I'm going to get some bad results because the CST triangle doesn't do a real good job of bending. Okay? Going to get better results the smaller I make my triangles, but it's not going to be as good as it could be. The result is the model is going to be stiffer than it should be. If it's stiffer than it should be, then the deflection at the end is going to be smaller than what I expected. Okay? But a concentrated triangle is going to be the simplest type of formulation that you can use. So the reason we use CSTs is because it gives us simple results. And as we start doing these analysis, you're going to have the ability to switch between CSTs and LSTs in SolidWorks. So the coarse mesh, I believe is the way SolidWorks refers to it. The coarse mesh or the rough analysis, I forget the terminology, we'll have to look at SolidWorks. But there's two choices. You can either do, I think maybe like a rough analysis and then a fine analysis. The rough analysis uses CSTs. The fine analysis uses LSTs, which are linear strain triangles. But the LST requires more time, more computing resources, more file storage, and so forth. Okay? So a linear strain triangle, the formulation is changed in that I have what's called mid-side nodes. So if I look at the element itself, I have nodes at the corners, and I also have nodes in the middle of each side. So if I have 3 points defining the side, that means that side can curve, right? So it has a higher formulation, a higher polynomial that is describing the side of that triangle. And as a result, then I have linear strain across the element, and that bending problem over there is linear strain, and so an LST is going to model that much better than the CSTs do. Now, something I haven't talked about very much is you guys need to, if you don't have the textbook that I recommended, you need to start reading the SolidWorks help. Okay? SolidWorks help goes through all of this and talks about how to set up the CSTs versus the LSTs and what that means. So you need to start, if you don't have the textbook, you have the entire online help for SolidWorks, and it goes through a lot of this same stuff that I'm talking about specific to SolidWorks. So if I tell you in the homework assignment, how do you set this up using a CST, then either remember what I said in here in class, or go to the SolidWorks help and look up the different element formulations. And then we'll show you similar pictures and talk a little bit about each element type. Okay? There's actually pretty good support built into the help that kind of explains this kind of stuff. For quadrilaterals, we have the same thing. The Q4 has 4 nodes, 1 in each corners of a rectangle. It has these similar problems to the CST in that the sides have to remain straight. So if we think about this, when this bends, this sides are supposed to curve in the reality, in the real object. In our model, because our sides have to remain straight, instead of them curving, they remain straight, so it looks like a parallelogram or a trapezoid instead of a curved beam. So again, the results are going to be too stiff. My displacements are going to be smaller than they should be. So to improve that, we have a Q8. Q8 has the mid-side nodes, so it's a rectangle, but it has 8 nodes. Should give you exact results in bending if the shape is rectangular. Okay? SolidWorks does not have quadrilateral elements. So we're stuck with the triangles. But other programs, there are, I think I've told you already, there are finite element programs that are only finite element programs. For example, that would be ANSYS. They're a higher end FEA. They have, you can choose between triangle elements and quadrilateral elements. Quadrilateral elements will generally give you better results. The problem is quadrilateral elements are harder to make when you have arbitrarily shaped objects. Obviously, if you have a big rectangle, it's really easy to divide that up into lots of little rectangles. But think about if you have a curved shape, it's hard to divide that up into little quadrilaterals without also having some triangles in there. It's very easy to take pretty much any shape and divide it up into triangles. You guys have probably done some of that with when we do the 3D printing, right? You save your file as a, like right now, what's
STL.
STL. When you save it as an STL file, it takes all the surfaces, it makes them into little triangles, right? Okay, we're doing kind of the same kind of thing. Is we're taking a surface or a shape and dividing it into triangles. Okay. What we are really going to be using, I call this plates and shells. In almost all cases, we are dealing with shell elements instead of plate elements. The difference between the two is plates are in plane loading only. Shells have the addition of bending, which would be a perpendicular force. So if I go back to my balloon analogy, a balloon is in plane only when I just have the pressure inside the balloon. Okay? Or a soda can is membrane only when you just have the pressure inside the can that's expanding the can. All of the loads are in the plane of the surfaces that are resisting it. That changes, however, if I take a balloon and then poke it with my finger. Think about that loading added onto. Then the surface of the balloon starts to undergo bending from my finger poking in against it. Okay? So if I'm going to model that, I have to actually use shell elements that have all 6 degrees of freedom for each node. Our plane elements, our plate elements only have the 3 degrees of freedom, which are the X and Y directions plus a rotation. So a shell element is what we're going to typically be using. A shell element has 6 degrees of freedom per node. So if I have a CST, do the math for me. CST is a constant strain triangle, has 3 nodes, right? 6 degrees of freedom per node. If it's a shell, gives me everybody's asleep. 3 nodes times 6 degrees of freedom is 18. Okay? So a CST has, if it's a shell, has 18 degrees of freedom. Notice that this picture here is the, would be just the plate. So it doesn't have the additional, so it just has the 2 degrees of freedom for the linear translations. Okay, if that's a shell, then it has 6 at each node. 6 times 3 is 18. If I use LST, how many degrees of freedom do I have? 36. 6 times 6. 6 nodes times 6 degrees of freedom is 36 degrees of freedom on each element. And the reason I'm bringing this up, because remember then, that tells you how big your matrices start to get. So one element's a 6 by 6. Multiply that by the number of elements in the structure, and that gives you the size of the matrix you have to solve in order to do the calculations. The quad floor has how many degrees of freedom if it's a shell? 24, and then the Q8 then has 48, okay? And generally speaking, the more degrees of freedom you have, the more accurate your results are going to be. Okay, so the best overall element for doing 2D analysis with shells would be a Q8, if your software supports it. For SolidWorks, our best case scenario would be the LST, element formulation. Okay? All right. How do I figure out what elements are in SolidWorks? If I just picked up SolidWorks and you guys didn't have me to talk to, how am I going to figure out what type of elements are being used? You read the help, right? Okay? Go look at the help and you'll see similar terminology, and it will talk about the different types of elements. That's going to be any software. Read the documentation and it will tell you what is the math that is backing up the calculations that it's doing. Okay? So I want you guys to start familiarizing yourself if you haven't already started using it. There's pretty good stuff in SolidWorks help files. All right, another little bit abstract kind of thing. When you combine different element types, you have to be very careful about how you attach them together. Okay, so remember I said that 2D plate elements have translational degrees of freedom, but not rotational ones. Well, what happens if I take that and attach a beam to this node out here? These elements in here only have X, Y, and Z degrees of freedom. The beam element has to have a rotational degree of freedom. So we essentially have a hinge here. And so if I attach this in together as drawn, this thing is going to be like a trapdoor that just falls down because it does not have those rotational degrees of freedoms restrained. So if you're getting weird results when you combine multiple element types together, consider what are the degrees of freedom that you might have. And do those elements support those degrees of freedom? So then there's ways to avoid that. So in this case, I could model this with my beams going back into the structure, which would then create that moment here so that the structure works. Okay? That's kind of an unlikely scenario, but I wanted to mention it in case you come up with some weird stuff out of your results. Okay, so we're going to start getting stress results. And so far, if you've been using SolidWorks, you probably have used just whatever the default stress results are. You have the ability to set up any type of stress results that you want. Okay? And I'm going to encourage you to start looking at those because they're going to tell you useful things about your solutions. Okay? By default, does anybody know what the stress values that are output are? Anybody notice? Okay, the default stress results, and this is going to get more important as we get to three-dimensional stuff. You're going to see something in there that says, and I've always pronounced this von Mises. I'm not completely sure that I'm correct in that. I will probably by default say von Mises because that's what I've been using for 20 years. I've also heard people call it von Mises. Okay, so whatever the appropriate pronunciation of this person's name is, I don't honestly know. Okay, but you will get von Mises stress. Von Mises stress is a three-dimensional combination of all of the stresses to give you an overall concept of what is the state of stress at each point in your structure. Okay? The stress is not something that we've dealt with before. The closest you've come with to this probably has been, you've definitely done sigma x, stress in the x direction, stress in the y direction. What did we do to combine x and y stresses? What do we call that? calculated principal stresses before, right? Does that ring a bell? So you can also output principal stresses. Okay, remember that? Sigma 1, sigma 2. Or you can also output just the stress in the x direction, stress in the y direction, stress in the z direction. And you can set up graphs that show all those. Okay, the default is it's going to come out the von Mises, because it kind of gives you an overall state of the three-dimensional object, and you can compare that to the yield stress and figure out if you've got a problem or not. Okay, so go back to our bending up here, and let's say that the x direction is this way, the y direction is this way, and the z direction is coming out of the page of the board. Okay? If I'm looking at stresses right here, what direction are those stresses actually in? In the x direction, right? We've got tension on the top here. We've got stresses that are pulling in this direction, right? So if I create a plot of the y direction stresses, what am I going to get? Probably nothing. Unless I have some, well, no, I will get nothing in this case, for this loading case. Okay? So, if I plot the x direction stresses and I plot the von Mises stresses, those two plots should look like identical. Values should be the same. If I plot the y direction stresses, I'm going to get zeros. So that's a tool that I can use to figure out what's going on if I've got something weird going on. Let's say you accidentally put a force that was in the z direction. You might be getting some y or z stresses, and you're like, where are these coming from? Well, that's an error checking thing. Okay, so this can be useful in plotting those different stresses. Another thing that is really useful is this energy norm error plot. So remember I said we don't get exact results? We need to refine our elements to reduce the error from one element to the next element. And so SolidWorks does a nice thing that is called the energy norm error. And I'm just going to tell you to try it and see what your mesh looks like. And we'll talk more about this as in a future week. Okay? But you can create an output that shows where do I have good results in my model and where do I need to do some mesh refinement. And that energy norm error plot will be useful to you for doing that. Okay? So, those of you that need to catch up on assignments, let's get those assignments caught up. Those of you that are working ahead a little bit, you might start playing around with some of these more advanced settings to get better results out of our models. Okay? All right, so that's what I have prepared for today. I'm expecting we're going to have to address this again as you guys go through these assignments. Some of you have been doing a really good job of coming and talking to me and asking questions. Some of you I haven't heard a whole lot from. So let's make sure that you're understanding what we're doing, why we're doing it. And I will continue to give you some feedback on your assignments. Okay? Any final questions? All right. Let's work on this stuff and let me know what I can do to help you out.